Okay, you ready? Put your phones away, please. Now, we are going to do sequences and series. They sound alike, but they are not. Well, they are. They got some similarities. That's the problem with it. A sequence is simply a list of numbers, and there's an order to them. And sometimes we can't see the order. It's just a list. That's all. So our first section is on sequences. So we're just going to be looking at lists of numbers in a definite order. So we could talk about a function whose domain is a set of positive integers. Do you remember what integers are? Whole numbers and their opposites. Now because this is a list of numbers, sequences are not continuous. They are not continuous. I can write. So if I had the function f of x is equal to x even, like it's pretty simple, then I'm going to write a sequence as a sub n, and that's equal to n. So this would be the function, and that would pick up all values of x. This is continuous. What's going to happen is we're going to find out the sequences behave like functions. What would the sequence be? And they put it in these little braces here. That means a sequence. Okay, so what would the first element be? Oh, I forgot to tell you about this. And these guys' numbers are always going to be whole numbers, not negatives. So there's no negatives. So the first element would be 0. What would the second element be? Member of the sequence, if you want to call it. 1 and 2. Okay, so I'm not picking up all the numbers. I'm only picking up the whole numbers. So if I wanted to graph that, which I didn't give myself a lot of space, but so if I wanted to graph y equals x, we know that looks like this, right? What does the sequence look like? It looks like dots, right? So if you're in stats, you kind of know what I'm talking about, right? Right, like a scatter plot. Well, what's interesting about this is a sequence will behave like the function that it's like most of the time. And then what we're going to do in the next section is we're going to add up the elements in the sequence, and that's called a series. And then you can have a series of partial sums, and then you can add those up too. So things get really complicated. You could talk about, I was just thinking about this, you guys all know the problem. You get paid what, a penny per day, and then that's day 1. And then next day, we're going to double it. So 2 cents per day. And then next day, we're going to double that. So what would that be? 4 cents per day. Because that's how you're going to set up your salary. So first day, I'm going to pay a penny. Second day, I'm going to pay you 2 pennies. Third day, I'm going to pay you 4 pennies. Do you want that, or do you want to get something like $25 per day? Constant. This is a sequence. Well, that's a good question. That's a really good question. How long are you going to work? When do you break even? Now, you have to think about this. This is the sequence. 1, 2, 4. What's the next one? 8. Okay, that's a sequence. That's all it is. But what are you going to do? I mean, you're going to take this money and you're going to put it in the bank. So really, how much do you earn? Well, forget the interest. So when does this sum get to be bigger than that? It doesn't take very long. If you keep doubling your salary, it doesn't take long. Even if you start out 1 penny. I'll let you think about it. Pardon? It's per day. Oh, well, I don't know where the break even is. Oh, you just wait. Well, you shouldn't be, you weren't that late. Oh, you shouldn't have been. Okay. Here's another one, you guys. You know, not everybody in here celebrates Christmas, but for those of us who do, and almost everybody knows the song, The 12 days of Christmas. So the first day you get a turtle dove. What do you get the second day? No, no, you get a partridge in a pear tree. Second day you get 2 turtle doves. But how many presents do you have now? You have 2 partridges in the pear tree. Remember, you have to keep adding them up because the third day of Christmas you get. What do you get the third day? 1 the first day, but no, you keep on the fifth day you get 5 golden rings, 4 French. You have to add them all up. I know. I gotta sing it to do it. I don't know it. Okay. So you don't just get 12 gifts or whatever. You got to be careful. There's a lot more than you think. After 12 days of Christmas, how many partridges in a pear tree do you have? 12. There you go. Okay, well, that's what this is all about. We're doing sequences and series. I like to give you the big picture. Okay, series are more important than sequences, but we have to do sequences first. Then, pardon? We could talk about the sequences there, but what are you really getting in terms of gifts? On the second day, you get another partridge in a pear tree, plus, what is the two turtle doves. The third day, you're going to get 2 more turtle doves, another partridge, and 3. Yeah, so how many how many presents you get in all? That's a series when you add them up. Okay, here's where I just want you to get the big picture. So the first half of chapter 8 is learning about sequences and series and when they converge, and we'll talk about convergence. Well, that's next. The second half is I'm going to take a function like e to the x, and I'm going to write it as a polynomial. And you might say, well, why would you do that? Well, because it's a lot easier to work with. I'm going to tell you that the polynomial for this one, and you're going to memorize this. Now, you probably don't remember the factorial symbol or have never seen it, so you'll tell me. Over 3 factorial. And you would be surprised that even with this few number of terms I have here, that's a polynomial. And if you graph e to the x and you graph that polynomial on the same screen, in a small window, they will be the same. It won't be in the whole window. I have to have an infinite number of terms over here to get it to be exactly e to the x. That's the second half. Those are called Taylor polynomials or power series. And that's a big thing. Well, the thing with power series is we have to know where they converge. So I have to do all these little convergence tests, even though it seems kind of senseless. Not yet. We'll get there. No, I just want to give you the big picture. Pardon? It is, but when you get there, it'll be okay. And what's nice about polynomials is you can find derivatives easily. You can integrate easily. Okay, yeah, the squeeze term's going to come back and haunt us. See, you can integrate e to the x, right? That's e to the x plus what? C. But what about e to the x squared? Those of you with a CAS calculator, you can't do it. So what I'm going to do is I'm going to use this polynomial approximation and substitute in x squared for x. But we'll do all that. And then I can integrate it because I can integrate a polynomial. These are all going to be whole number exponents. They behave nicely. There's no breaks in the graph, Ori. Okay? There's no holes. There's no asymptotes, nothing. They're very nice. But we'll get there when we get there. But that's the big picture to see where we're going. Well, to get there, I have to know when that converges. So let's talk about convergence. Okay. The elements of the sequence are called a sub 1, a sub 2, a sub 3, a sub n. Now, does this have a limit? 0, 1, 2, 3, 4, 5, or does it just keep increasing without bound? What is this going to go off to? Infinity. So we have no limit here. Now, the rules for finding your limits of sequences is different than your limits for series. And that is nice about the CAS calculator. It'll do both. Okay, so we say the limit of our sequence is L as n goes to infinity. It's just like saying, it's like taking the limit of a function as x goes to infinity of x. We know that that's infinity. What would this look like? In sequence notation, it would be the limit as n goes to infinity, because n represents whole numbers, and this would be n. That's also infinity. Okay, that's said to be divergent. Let's look at another sequence. Let's look at this sequence. Sequence of 1 over n. It has a special name. Everybody knows it. It's the harmonic sequence. Unfortunately, it causes us a lot of trouble. What does that sequence look like? And we're going to start with 1, because 1 divided by 0 doesn't work. So it's 1, 1/2, 1/3. Okay, Eric, pay attention so you know what you're doing here. What's the next one? 1/4, 1/5, 1 over n. What is that limit as n goes to infinity? That's 0. That's said to converge. So if this is some value, L, this converges. And we're only going to be talking about positive terms to begin with. Positive terms. Eric, pay attention. Because you're already here for 1 hour. You don't want to watch the video again for another hour, do you? No. I don't think so. You got a lot of stuff to do. Convergent means that it has a limit. There's a limiting value. If I keep closing the door halfway, does that converge? Yeah, eventually the door gets closed. Same rules for limits apply. So you could, if you wanted to, if you don't see this, you could go to the function, and there's a theorem about that, and take the limit as x goes to infinity of 1 over x, and we remember that's what? 0. You won't have a problem with a lot of these. And the first day should be okay. Notice I assigned 1 through 16. Shouldn't even take you very long. You're going to find the limit of sequences. Some will be trickier. When in doubt, write out the terms. Okay, so if a limit exists, then the sequence converges. That means that sequence will go to a value. Now, whether it's 0 or a number is going to be significant later on. If the sequence is divergent, we kind of like that because then all of our work will be done. I like them to diverge because I don't have to do anymore. But when I do those Taylor polynomials, it's not going to work that way. Okay, do you understand the difference between converge and diverge? That's a big thing, actually. Okay, and I think I have this theorem in there twice. And it looks terrible. And when you major in math, that actually looks way better than what you see when you major in math. But if it looks kind of scary, that's what the real mathematics looks like at college. I do want you to know that. If somebody told me that, I wouldn't be standing in front of you. I'd be doing engineering probably. But I got through it. So if the limit of my function has some value L, and the function's continuous, that's how it relates to the calculus. That's about all. And they are basically saying if your limit of your function is L and you can write your sequence, how did I say that? Your sequence, I wrote it down the way I wanted to say it. I want to say it matches up with the function. I wrote it down someplace, but I'm not sure where. There it is. So if you can take a function, f of x, and you write it as a sequence, then the sequence and the function have the same limit. The sequence and the function have the same limit. You won't even think about it. You'll just do it. It will be converting the sequence into a function. So if I had this one, 1 over n squared, what would that function be? So if you can do that, when we get to factorials, you say, well, why can't I always do that? Well, what's 1 over n factorial? I can't write that as a function because it's not. Right, I don't either. So that's when our problems are going to become more difficult, when we get the factorials involved. We'll define that in a second. Now, my page numbers are probably wrong. Sorry. And we're going to use the squeeze theorem again. Yeah, it's going to be okay. And you remember the squeeze theorem? Well, it's not that bad. It's right here. Know your limit laws, limits distribute. Just it's the same stuff you already know. You're just going to apply this to a list of numbers, not a continuous group of numbers. Let's just do the squeeze theorem for functions because it's going to be easier for me to draw. It's the only reason. So you have some function or some sequence, a sub n. Oh, maybe I'll do it this way. There's a sub n. Remember, because these are just numbers. And then you have another one, c sub n. And let's see, I'm trying to get together there. Okay, there's my c sub n. And my b sub n is trapped between a sub n and c sub n. Then what do you think about the limit of this one? If this limit is L and this limit is L, what do you think about b sub n? Yeah. The hard part is figuring out what to trap it between. Hopefully one will be 0. And if you can show that the other sequence goes to 0 wherever you're looking, then b sub n is trapped between them. It's going to have to also be 0. So remember the squeeze there? Except now we don't have functions. I'm trying to make it so you can see it a little bit better. And we can do that. Maybe tomorrow we'll do our calculators and show you how to do sequences on your calculator because you can do them. So by the time this year ends, you know how to do all those little functions on your calculator. Okay. Here's a big theorem. You have a lot of these to learn, I'm sorry to say. And they all kind of look alike. That's the other hard part. If the limit of the absolute value of my sequence is 0, maybe should I write it? If the limit of the absolute value of my sequence is 0, then the limit of the sequence, which in this case could have some negative terms, but the limit of the sequence is also 0. Yeah, 0. Oh, yeah, sorry. Doesn't work for other numbers. Only works for 0. So I'm going to put this only for 0. I'll let you think about why that has to be just 0. Because if you get the limit of the absolute value is a number, I don't really know much about the original one. Yeah, we're going to do some. Yeah, we're going to do some. Just want to make sure. Oh, there's some other sequences. Okay, so ready to look at some examples?
Yeah.
Now, I can go back to functions. This is the same as this problem. These are like horizontal asymptotes, that's all. Do we know the answer to that one? It's a horizontal asymptote. Is there one? As x gets to infinity, remember, we don't care about the 1. So this is equal to what? 1. So this is equal to 1. Are you going to write this out? No, you're just going to write the answer. That's okay. It's fine. What? Asymptotes?
Yeah.
Oh, no, we don't want to do that. Okay, that's as hard as some of the homework is. But you need to practice with it so you recognize it. Is that all I got on that one? Yeah, I put mine 1 per problem per page. Ready? This one's trickier. I'm going to compare the natural log of x to x. So I'm really going to do this. The limit as x goes to infinity, and it's the log of x over x. And here's where your intuition is going to pay off. I can't do it algebraically. I just have to know who's winning, who grows faster, the log of x or x. Well, I know, that's the thing. I don't think you do know. So let's graph y equals x, because we can do that easily, right? Here's y equals x. Approximately. And I'll do this. The log of x, remember what that looks like? It looks like this. So you need to know what these look like. So who's overpowering the other, x or log x? It's the x, so this is going to go to what? 0. Even if you're talking about the log of 100, that's like 12. And you could graph it if you want me to. What's my time? I know you want to look at your test, so I don't really have time. We could graph it. So what's this limit? It's 0. Is that all you're going to write? Probably. That's probably all you're going to write. There are going to be some tricky ones. So you need to know that the log of n is less than n. What, you guys, you know what happens if I reciprocal this? Eric, do you know what happens when I reciprocal this? This is 1 over log of n, and this is 1 over n. How does the inequality change, or does it stay the same? Duncan, do you know? Eric, if the log of a number is less than the number, what if I find the reciprocal of these? Does the inequality stay the same, or does it change? It switches. Put some numbers in and make sure I'm right. These you need to know. These will show up, and by the way, all of this will be multiple choice. Sections 8.1 through 8.4 will all be multiple choice questions. They never ask this question in the free response. I can't even come up with free response questions. So your test will be multiple choice on this part. And they may have something where you have to know this. And in fact, I know they do. Okay, let's get some more problems. Oh, and some of you like L'Hopital. Now, we should do L'Hopital, and I don't know if I have budgeted in there, but I can try. But L'Hopital says if you have a fraction, this must be a fraction, and you have 0 over 0, and proving this is really hard to prove, but the limit of this fraction is equal to the limit of the derivatives. So if we had the limit as x goes to 0 of the sine of x over x, we've memorized that to be 1. But L'Hopital's rule says that I can do this. Now, first off, when you apply L'Hopital's rule, you must say 0 over 0. That was my first year of grading. And if you didn't say 0 over 0, you didn't get any of the points, even if you had the right answer. Okay? Marshall, you got that? You have to say 0 over 0, because if I don't get 0 over 0, L'Hopital's rule does not apply. Has to be 0 over 0 or infinity over infinity. There's a bunch of other things. But for right now, that's all we need. Okay, so all I have to do now is take the limit of the derivatives. Not the quotient rule, just the derivative. What's the derivative of sine? Cosine of x over 1. Now you always evaluate right away, and this is equal to the cosine of 0 over 1, which is 1. There you go. You may only use L'Hopital's rule if you have a fraction. We'll deal with it later on this year. What happens if you have a subtraction and stuff like that? Okay. It has to be a fraction. It has to be some function over another function. And you have to get 0 over 0. It's not the quotient rule. It's the ratio of the derivatives. You just have to know the theorem. It's a limit. It's not a derivative. It's just saying that when you look at the ratio of the limit of these two functions, all you have to do is look at the limit of their slopes. I can't prove it. I can prove it at the origin easily, but elsewhere I can't. I just took the derivative of the sine, which is cosine of x, divided by the derivative of x, which is 1, and then I evaluate. It's only limits. It's not derivatives. Derivatives are involved. Yep, we did it last year. Why do I have two things in my hand? I have to get 0 over 0 or infinity over infinity, and there's a bunch of other ones, but we're not doing those. These are the only ones you have to know right now. Okay, Eric, worry about it later. I did this theorem. That's all. If you want to find the limit of this sequence and you can write it as a function, and that limit is L, then that limit's L. I already did that. I don't know why I have it twice. Okay, what about that one? Now, this is what we call an alternating sign, and you're going to see it a lot. All it's doing is alternating the sign. And we will start, with 1. We'll start with n equal to 1. Sometimes you can start with 0, but we'll worry about that later. So it's negative 1 to the first, negative 1 to the second, negative 1 to the third, negative 1 to the fourth. So this is negative 1, 1. Does it converge? Has to be a single value. Now, some of you may be saying, well, why don't you apply the absolute value theorem? Remember the theorem has said, if the absolute value of this is 0, then the limit of this is 0. And I said it only works if the absolute value is 0. It doesn't work if it's some other number. Because if I take the limit of the absolute value of this, of negative 1, to the n as n goes to infinity, that's equal to the limit as n goes to infinity of 1 to the n. That's what? 1. That one exists. But the theorem didn't say that. The theorem said it had to be what? Where is this? It had to be 0. See, it's only for 0. It's easy to fall in the trap and say it applies all the time. It does not. So I can't use that theorem to do this one, so I just made a list. And a list works. So if you don't know what to do, write out some of the terms, and it should show you what to do. And there's some really hard problems in this section, but we aren't going to do those today. The first 16 should be okay. Some of you may say, I don't need to do them. Yeah, you do. Because it's like probability. I give you one problem, and then I'm going to give you another problem. It's very different, and you can't say, oh, you always do this. That theorem does not apply. Theorem 1, I think, does not apply. It has to be a limit of 0. And we know this diverges. This is 1, negative 1. I'd like to say if it went to 2 values, it converges, but it doesn't. It has to go to a single value. And we're almost done. How about that one? Well, you can write out the terms. So if we start with n equal to 1, it's going to be negative 1 over 1. Then it's going to be 1 over, what's n next? 2. Then it's going to be negative 1, because this is going to alternate the sign in the numerator, over 3. Negative 1 over, positive 1 over 4. Can I try that theorem on this one? Is the limit of the absolute value of this, is that 0? As n goes to infinity, that's equal to the limit as n goes to infinity of 1 over n. There's that theorem. I'm going to do the absolute value. The absolute value, that's just 1 over n. N is always a positive number. This is 0. The theorem says that if the absolute value, the limit of the absolute value is 0, then the limit of this is 0. And if you think about it, if you were to graph these points, we are going to start at negative 1. Here's 1. And then I'm going to jump up to 1/2, which is right there. Then I'm going to jump down to negative a third, positive a fourth, negative a fifth. Can you see that they look like they're converging to what? 0. It only works with 0, so it works here. So we're fine. And that's all you're going to do, is probably write down just the answer.
Wait, so for that first example 5, so it goes -1.
That one?
The same distance.
Yeah, don't do that. Is this one, if I wanted to graph this, this is starting at negative 1, positive 1. Negative 1, positive 1. It's jumping up and down, but it's not ever going to a value. Keeps alternating sign. So let's do the squeeze theorem. This is the last one. It's not on your handout, I don't believe. But let's try this. And what you look at this as, and I forgot to study this one, but that's okay. You look at that, it looks like what? It looks like 2 over n, doesn't it? Well, let's see. What's this going to be? Let's write out some terms. So n is equal to 1. So it's going to be 2 minus 1 over 1. Then it's going to be 2 plus 1 over 2. If I don't know what to do, I'm going to write it out. 2 minus 1 over 3 plus, whoops, sorry, comma. 2 plus 1 over 4. 2 minus 1 over 5. 2 plus 1 over 6. It's probably enough to see what's happening because it's going to be multiple choice. But this is 1 half, 3 halves, 1 third, 3 fourths, 1 fifth, right? And 3 sixths. Can I, what? 2 minus 1. Oh, yeah, right. So what's it trapped between? Is it trapped? Between 0 and, so what if we took 40? So I have 40 itself will be 2 plus a negative 1 to the 40th over 40. So what's that going to give you? That's 1/40th. And then what if I do the 41st? It's 2 plus negative 1 to the 41st power over 40. So it's what? No, this was supposed to be 3 over 40, right? This is what? This is negative. 2 minus 1 is 1 over 41. So it's trapped to 0. It looks like the maximum. It looks like it's less than or equal to 3 over n. Okay. So I had to figure out what it was smaller than. Could you make it 5 over n? Yes. All you have to do is find an upper bound. That's it. And what's the limit of this guy? 0. The limit of this one is 0. Therefore, this must be 0. Now, on my multiple choice, you have to justify your responses because I need to make sure you know all the information. On the actual exam, you may guess. Don't ever leave anything blank. Could I do 10 over n? 100 over n? It's clearly less than that. I could do 1,000,000 over 10, but 1,000,000 over 10, or n, still goes to 0. There's only one problem in the assignment, so you better try it. This is obviously positive.
It wouldn't be equal to it, would it?
Doesn't matter. It's a limiting value. Okay. So, which one do you want to just see today? On your tests. The individual or the partner?